Hello viewers, in today's video we'll be learning about the steady state response of a 1 degree of freedom system when it is subjected to harmonic force function excitation. So here on the left we have the representative system comprising of the stiffness, damping and mass element, which has been subjected to a harmonic force function whose magnitude is the maximum amplitude is f naught. We can say that we know the behavior of this system when we can describe the instantaneous displacement represented by small x here at any given time t. The response of this kind of a system comprises of two components. Mathematically, the first one is given by the complementary function, which is a transient function which diminishes with the passage of time. The second one is a particular integral, which is the steady state response. So in today's discussion, we'll be discussing only the steady state response component. And on that, we'll be concerned mainly not with this instantaneous displacement, but rather with the amplitude of the instantaneous displacement. That is what we'll be determining here. This is given here in this cell, F7. So I'll be selecting each one of these cells independently, and you can see the corresponding expression, the formula here in the formula bar. So in case you want to develop your own sheet, that way that will be possible. So I've divided this sheet into multiple sections. One is this input section highlighted in light brown. Then we have the intermediate calculations, and here on the right I have the output section, which is being plotted in these two plots on the bottom. Okay, the symbols have their usual meanings. This is T stands for time. I've just made it like this so that this angle omega t remains constant. So it doesn't have much significance in as far as the calculations are concerned in this particular simulation. So omega is the frequency in radians per second of the imposed force function, which is harmonic in nature. K is the stiffness of the spring in newtons per meter. I have used SI units in this entire worksheet. C is the damping coefficient in newtons per meter per second. M is the mass. F naught is the amplitude of the externally applied force in newtons. So here we have the cyclic natural frequency again in radians per second, the critical damping coefficient, this is the damping factor or damping ratio. Here comes the amplitude of the oscillations undergone by this mass m. Then we have phase angle phi. This is a bit tricky. So at times when both the numerator and the denominator in the tan inverse function are negative, this angle phi value, the tan inverse, gives a misleading value. In that case we have to add 180 degrees or pi in this case. So you can note down this expression and then make it accordingly. And this xst represents the zero frequency deflection. That is nothing but f naught divided by this stiffness component k. Okay, now in the output section we have this f naught is nothing but referring to this one. So I'll be highlighting each one of these. You can just quickly see these are the ones which are used for drawing these vectors. Just see all the expressions in the formula bar. That will facilitate you to make a similar sheet on your own in case you so desire. Okay, now this is just a duplicate of it for this triangular representation of the three vectors. Okay, so I'll be changing this frequency of the force F. So I'll be changing this omega. You can just see this omega in relation to the natural frequency of the system. So right now is less, so omega upon omega n gives you the frequency ratio. Right now it is less than 1. When this becomes 1, it will be resonance. So here I am going to increase omega, and you can see its effect on the resulting vector diagram. So I'll increase it a little bit so that you can see the various force components. So here in this diagram on the right, we have this vector is F naught. The legends are given at the bottom of the charts. This red vector is representing the spring force, this green one is representing the dashpot force, and the blue one is representing the inertia force. So as we keep increasing omega and as it approaches the natural frequency, you see the phase angle phi is undergoing a change. As omega approaches omega n, phase angle phi undergoes a very abrupt change. The rate of that change also depends upon this damping factor zeta, or in other words, this damping coefficient C. So when zeta is small, the change is more abrupt. When zeta is large, this change is less abrupt, that is more gradual in that case. So I make omega 0.9. Now the ratio is just 0.9 by 1, that is 0.9. You see phi is approaching 90 degrees. So when this is 1, yes, this becomes 90. This angle phi is approaching, it has become 90 degrees or pi by 2 radians. Now in this situation, this force, the external force F naught, is being opposed by the dashpot force or the viscous component. At the beginning, when omega was small, you might have noticed, I make it very small, when the imposed frequency is very small, the externally applied force is being balanced, countered primarily by the spring force. Now as we go beyond the resonant frequency, so I make it 1.1, the diagram again changes shape, I make it 1.5, and I quickly move towards higher values of omega, I make it 2. Now you can see here, it is the inertia force that is now going to oppose primarily the externally applied force. I make it 5, and now you can see the direction in which it's leading. And so at very high imposed frequencies, this mass will simply refuse to budge from its place. So the components of forces shared by the spring or the dashpot, they become very, very negligible. So that is how it goes. And because this inertia force is always opposite to the spring force, see, this is the inertia force, this is the spring force. So in the figure drawn on the left, I have just subtracted the inertia force from the spring force. So instead of a quadrilateral, we get a triangle here. So that gives another insight into how these forces are going to behave. So I hope this video has been helpful in developing an insight into the response of a 1 degree of freedom system. Thanks for watching.